Hello everyone. So welcome to the channel GG Physics by VG sir. Okay, so in today's class, I have taken one very important question, a very good question. So from that question, we can understand some very important points regarding magnetic flux as well as a solenoid. Okay, so the question goes like this. So first, I am reading this question. So they have given a solenoid, so for which they are telling length is much greater than radius. So that means basically they are telling that so consider that this is a long solenoid. Okay, so the first thing that they are asking us to prove is magnetic field at the end point is half of the magnetic field inside. This is the first point that first one that they are asking us to prove. And second one is magnetic flux through the end phase is half of the flux that is inside. And the third one that they are asking us to do is the field, the field line, the crossing the endmost winding is straight line perpendicular to the axis of solenoid. So we'll see one by one. Okay, so first let us do this first part and try to prove this the first one. So the first one, so they're asking us to find the magnetic field at the end point P. Okay, so to understand this, so we can do this in two different ways. So the first one is, let us consider a solenoid like this. Okay, let us consider this a solenoid, very long solenoid, and let's say the windings are designed in such a way that, let's say here out of the plane, the current is coming out of the plane. The windings are designed, they are equally spaced. Okay, so the number of turns per unit length is given as let's say small n, and here the windings are going. Okay, basically the current is going into this plane, so like this. Okay, now for long solenoid, you guys already know, let's say this is the axis of this solenoid. Let's say this is the axis of this long solenoid. So we already know the magnetic field inside a long solenoid is uniform, right? So again, the proof of that I am not discussing here. You guys know how to solve it by taking rings over here, and we know what is the formula for magnetic field due to a ring on its axis, and by deriving that you will be getting the formula. Okay, so the B inside, okay, so inside a long solenoid somewhere over here will be equal to, we already know the formula, which is mu naught Ni. But now the task is we need to find the magnetic field at the point P, and basically we need to show that the magnetic field at the point P is half of the magnetic field that is at the like middle or inside the long solenoid, right? So first I'll directly use the formula that you guys know from the derivation, whatever you will be getting. So what is the formula you will be getting from the derivation? The formula is B inside. Okay, let's say instead of like considering it as a long solenoid, basically here it is a long solenoid. Let's say if it is not a long solenoid, the formula goes something like this. Let's say we need to find at some point X, we need to draw the perpendiculars over here, and let's say this is subtending an angle alpha and this is subtending some angle beta. So the formula goes like this: mu naught, this is not B inside, this will be B, this will be the B magnetic field at the random point X. So that will be given as mu naught Ni by 2 into sine alpha plus sine beta, right? So this is the formula. So if it is at the end point, so basically I have given magnetic field at any random point X, right? So if you consider the P point over here, this one, this diagram, for this one you need to understand that this is the perpendicular. So for this one, you guys need to understand for point P, alpha is what, 0 degrees, and beta, as it is a long solenoid, beta is what, 90 degrees, right? So by using this, so directly we'll be getting magnetic field at point P as mu naught Ni by 2 into sine 0 plus sine 0 degrees plus sine 90 degrees. So therefore magnetic field at P which is equal to mu naught Ni by 2, which is nothing but what? Magnetic field inside this long solenoid by 2. So therefore we have proved it. So magnetic field at the point P is nothing but half of the magnetic field inside the long solenoid, right? So the first one is done. So the same thing we can also do by like the principle superposition principle as well. Okay, by considering a symmetry. So in that manner also we can prove this. Okay, so let us try to prove this second point now. Okay, so the second point here that they are asking us to find is or like prove is magnetic flux through the end phase is half of the magnetic flux that is inside, right? So now to prove this point, I'm going to use the principle of superposition, which we would have used in deriving or in proving the first point as well. Okay, so the point goes something like this. So let me copy this diagram as it is. Yeah. So to solve it, so let me take two different solenoids here, identical solenoids which are carrying same current. Okay, which are both the solenoids are carrying the same current as well as same number of turns as given. So basically like two identical solenoids I'm taking. Okay, so one is this one. Okay, so let me copy this, and this is the second one. Okay, so both are like completely identical solenoids. The current is same, number of turns is same, everything is same. Okay. Now the most important thing is, so you guys need to understand from here. The first proof you need to understand that inside the magnetic, inside the solenoid, because of the entire symmetry, the field will be uniform over here. Whereas the field, okay, the field that is at this end, so will not be uniform, but at the center because of symmetry from both the sides it will be uniform. And when it comes to the end, okay, when it comes to the ends of the end of the solenoid, the magnetic field is no longer uniform, right? So that means, so basically the magnetic field lines will be something like this. Okay, the field lines will be, so basically they won't be, no longer there'll be straight lines at the end, so there'll be something like this. And some field lines might go like this, and whatever the field lines that are leaving from here, they'll be again entering from this side, because magnetic field lines they need to complete full loop, right? So always magnetic field lines will always exist as what, closed loops. So they're leaving from here and they'll enter from here. Same thing, the mirror image goes here as well, like this, like this. And on the axis obviously it will be along horizontal like this. Okay, and some field lines will be entering here and they'll be leaving here, and some field lines they'll go like this. Okay, so I hope this diagram is pretty much clear for you. And the mirror image of this will be again here, whatever the field lines that are drawn here, the same pattern that will be repeated over here. Okay, when I join these two, the like most important thing that you guys need to understand is the field lines over here is same as what, however the field lines that are present over here, right? So if I take this line over here, okay, try to understand this line I'm just drawing over here. Let's say that is this line. Now let me call this is a right side solenoid br, and this is a left side solenoid. Due to right side solenoid, you guys can see the field lines at this point, at this left end, they'll be like this, right? This is due to right side solenoid, right? And because of this left side solenoid, the field line at this end, okay, this is nothing but this intersection over here. So I'm clearly writing here. Okay, this is the intersection of intersection line. Okay, intersection line for when we join these two solenoids, the line that the line of intersection I'm just drawing here. This is the magnetic field due to what? The right side solenoid, and the magnetic field due to the left side solenoid, how it will be? So as I said, it will be same as this, whatever that's happening the right side or here, the same thing will happen over here, right? So the field line will be something like this. That means this is how it will be there. It will be like this, right? So this is B left, and magnitude wise it's like due to symmetry the magnitude wise it will be same. Okay, direction it is different, but magnitude wise it is same, right? So let's say this angle is some theta, so this angle will also be theta. As I said, magnitude wise both are same, right? So as magnitude wise both are same, so simply magnitude wise, as I said, due to symmetry BR will be equal to what? BL. So if you understand, if you clearly see over here, the vertical components will get cancelled. When both the solenoids are joined, the vertical components will get cancelled. And what will happen when we join these? Okay, so this is the center line over here. When we join these two, now the field lines at the center, they'll become what? They'll become uniform. Field lines at the center, this intersection line only again I'm drawing over here. This is the intersection. Okay, now the field lines have become what? Uniform. So in a uniform solenoid, long solenoid, we already know what is the magnetic field, right? Inside. So that is mu naught Ni. So if you understand here, so as I said, the vertical components will get cancelled over here. But what about the horizontal components? So B along horizontal, okay, B along horizontal is nothing but B along horizontal is nothing but what? It's nothing but 2BR, I can say, okay, you can say 2BR cos theta, sorry, 2BR sin theta, because BR and BL are same. So 2BR sin theta is nothing but what? B horizontal. So therefore, this theta you need to understand, it will vary, right? So this theta is completely variable for different lines that I'm going to take over here. Understood? So instead of taking this BR sin theta, let me write that as, so B, let me write it as B parallel. So therefore B net, let me write here as B net. When both are joined, this is net magnetic field. So therefore net magnetic field, I am writing it as 2 times of B horizontal. Okay, BH or B parallel, whatever. B horizontal I have written, and BR sin theta is nothing but B horizontal. And BR cos theta and BL cos theta, they'll get cancelled. And this 2BH will be equal to what? B naught, whatever the B naught value that you know, which is nothing but what? Mu naught Ni. So that means from here, you guys need to understand the horizontal component field is nothing but what? B naught by B naught by 2. So this is very, very important. Okay. So here, non-uniform field lines will be there. That's pretty much clear for us. But for that non-uniform magnetic field, you guys need to understand that this is very, very important. The horizontal component of that, whatever the magnetic field lines that are present at the end, that will remain constant, which is nothing but what? Half of this, half of the whatever the field that will be present at, half of the whatever the field that will be present at the uh, present inside the uniform solenoid, right? So this is very, very important. So to understand this, to solve or to prove the second point, what they're asking the second point, magnetic flux through the end phase is half of the flux inside, right? So what is the flux inside? The flux inside I can write like this, right? The flux inside can be written as B naught into, let me take this radius as what? Smaller. So B naught into, as the field lines are cutting normal to this surface area, whatever we will take here, okay, the circular cross section that we will be getting over there. So simply I can write B naught times what? B naught times pi r square. This is the flux inside, right? And when we come to this leftmost end over here, as we clearly know, the field over here is non-uniform. Okay, the field over here is non-uniform, and area of cross section will be like this. So to get the flux, obviously we need to know, here we'll be having two components, right? One is horizontal component, another one is vertical component. For every field lines we'll be having horizontal component as well as what, vertical component. And so to calculate the flux, we need to find the field lines which are like what. Okay, flux is nothing but b bar dot a bar, right? So indirectly we need to take b bar along what, area vector. So that means indirectly we just need to take the parallel component of the magnetic field lines. No need of bothering about what, this perpendicular field lines whatever that are there, because they will be along that surface through which we need to calculate the flux. So that means the flux that will be at the ends, the flux that will be at the end can be simply given as what, the flux at the end will be simply given as, so b horizontal multiplied by area, right? Area is pi r square, and b horizontal already we have got it as what, b naught by 2 into pi r square. So clearly we can see b naught pi r square, b naught pi r square is nothing but what, flux inside. So therefore flux at the end will be equal to half of the flux that is present inside, right? So this is also a very very important insightful result that we have got. The flux at the end will be half of the flux that is present over inside. Okay, from here now you will get a better understanding or clear idea about why I have taken the field lines out from here itself, not taking them completely outside. I have taken some of the field lines, they have directly going out of the solenoid through cutting the body itself. So the reason for this is, from this formula we can clearly understand that what is the reason. Flux is, basic definition for flux is nothing but number of field lines that are cutting. If you consider a cross section area over here, the flux is, let's say, phi in, but when you consider the flux through this one, it is only half, right? That means only half of the field lines are, whatever the field lines that will be coming from here, in that only half of the field lines are coming out. What about the other half? The other half, the field lines are going through this body, they're not even coming to this whatever the end area is there. Okay, so I hope it's pretty much clear. So this is also very insightful result, so proving that the magnetic field lines, all the magnetic field lines that are present inside, they won't be coming through this opening of the solenoid. Some of the field lines, to satisfy this result, so they must go through cutting the body. Okay, so I hope this is pretty much clear for you, and it's a very insightful result as well. Okay, so now let us go to this point number 3. Here the field line crossing the endmost winding means this one, whatever the line of this intersection line that is there, at this end they are asking us to prove. Okay, at this end they're asking us to prove the magnetic field line is like what, winding is straight line. The field is a straight line perpendicular to the axis of solenoid. That means they're asking us to prove that the magnetic field at this end is what? Perpendicular to the axis. That means simply they're asking us to prove that it is vertical in direction. Okay. So see, so something in physics, it might be very difficult for us to prove in a direct manner. So sometimes there is one more beautiful way of like solving and proving things in physics. So that is, so we'll do that by the help of contradiction method. Okay, so contradiction method means, first I'll consider that the field line is not perpendicular. Okay, not perpendicular to the axis. That means, so obviously the field line, let's say this is the intersection line, again I'm telling, this is intersection line or the end line, I can say. Now I am not joining them, right? So let me call this end line, let me call this is end line. Or, so to understand the superposition theorem, or to understand or to convert this randomness into like what, a uniformity, I am joining. See, actually when you have one solenoid, the field lines are completely At the end they are non-uniform, right? At the inside the solenoid they're uniform, but end they are completely non-uniform. To convert this ambiguity, or to convert this non-uniformity into uniform manner, I'm joining one more identical solenoid, which is helping us to create a what at the junction also. Like now the end will become the midsection of the long solenoid, so at that point we'll be getting a what uniform magnetic field, right? So this, if I consider one solenoid, I can say this is end line. Or else if I consider this intersection to like what to get that uniformity, I can also call it as what intersection line. I can also call it as intersection line, right? So let's say the magnetic field is non-uniform, sorry, not non-uniform, obviously it's non-uniform for one solenoid at the end. Let's say it is not vertical, we need to prove it is a vertical, right? Let's say it is not vertical, that means instead of being like this, let's say it is in this manner at the end, okay, at the end. So if it is in this way, okay, if it is in this way, so you guys need to understand. So here, okay, so if it is like this, obviously here it should be in what direction? It should be in this. It should be in this direction, right? So that means, so whatever the same way, whatever I have drawn here. So here already I have drawn, right? So you need to like you might get confused over here a bit, sir. Like already you have to drawn that the field lines are at some angle, no? So again you are asking me to like prove that here the field lines will be vertical. See, this is one of the field line that is coming through, coming out of the solenoid. So this theta indirectly we need to prove that this theta for this end line will be equal to what 0 degrees. This whatever the diagram that I have drawn, it might not be like for the what end line. So this is for some magnetic field which is coming from here. Understood? So basically we need to ensure that the field line that is coming from this end is like what perpendicular to this axis, perpendicular to this axis. So when if you take, if you consider that field lines are not perpendicular, if it is in this manner, okay, so then you need to understand, let's say this is b1, let's say this is b2. Basically this both the field lines are like what outside. But one very important thing that we know, due to symmetry, let's say this angle, again I am not taking alpha, let me take it as gamma, let me take it as gamma. So here b vertical will be equal to 0, but b horizontal is not equal to 0, right? So obviously because this b1 sine alpha and this b2 sine b1 sine delta and b2 sine delta both will be added up, right? So that means b horizontal is not becoming 0, but these field lines whatever I am considering, okay, these field lines whatever I am considering, these are at the end of the solenoid, right? These are at the end of the solenoid. Basically let's say at this point I'm going to find the magnetic field. When I join these two, so this point becomes what, this point, let me name this point as, let's say, uh, q, and this point as what q dash. Now both the points have joined. At the q the field is not 0, at the q dash the field is not 0 when the solenoids are separate. Then when we join both of them, let's say this point is what, that q or q dash, q or q dash. So this point now becomes for this solenoid as it becomes an outside point, right? This point becomes an outside point for this solenoid. So b horizontal is what not equal to 0 over here, because these two will get added up. That means, but we know, but we already know that we already know magnetic field outside solenoid will be equal to what 0. Magnetic field outside must be what 0. That means for this to happen there is only one possibility. That is what, this b horizontal should become 0. What is b horizontal? B horizontal is nothing but b horizontal b horizontal is nothing but magnitude wise b1 and b2 are same, right? So I can write 2b1 sine gamma. So for this to become 0, For this to become 0, there is only one possibility, which implies the gamma value must be equal to what? 0 degrees. So gamma equal to 0 degrees means, what does this mean? Gamma equal to 0 means what does this mean? This means field line, okay, field line at the end, at the end of a long solenoid, of end of the long solenoid, will be perpendicular to the axis, will be perpendicular to the axis. So this is also a very insightful result that we have derived, right? So by contradiction method, I have proven we have proved out here. Okay, so basically, by considering that, what if they are not perpendicular, what if they are not magnetic fields at the end are not perpendicular. So by taking that point, we have got a contradiction that the magnetic field is non-zero here. But we know the magnetic field outside for a long solenoid is zero. For that to happen, this gamma value should become what? Zero. That means magnetic field line at this end will be what? Perpendicular to this axis, whatever that is present. Okay, so I hope this third one is also clear for you. Now going to the fourth point that they're asking us to prove, that is a line in the center region at a distance r from the axis exits from the end at a distance of what? Root 2r from the axis. So this is also one very important point, so which can be proved by the help of magnetic flux concept. Let's say this is the solenoid that I've taken. Now let's say this is the axis that we have. This is the axis that we have. Now let me take a field line over here. Let me take a field line over here. Okay, so which is at a distance of what? Smaller. So inside it will be uniform, and we know obviously when it comes to n, it will become what? Non-uniform, like this. Now when the line is exiting this solenoid, we need to find at what distance that is there, right? This is the distance I need to find. Let me take this as r dash. Here the very important concept is, in between these two lines, we know there will be what? Many field lines that will be there. But we are pretty much sure that whatever the field lines that are present over here, they must cross this one, right? They must cross this whatever this cross section that is there, right? So that means, if you consider a cross section over here of radius r, and if you consider a cross section of radius r dash over here, whatever the flux or whatever the field lines that are crossing through this cross section of radius r, the same field lines or the same flux must go through this what? This radius of what? R dash also, right? So from this, that means flux at the middle from this cross section will be equal to, okay, flux at the end. Okay, not, this is not a general result, okay, for the cross sections that I have taken. So clearly I'm writing again. You might be thinking that, sir, in first second point we have proved that flux at the end is uh, flux at the end is half of the flux from in the middle. See here clearly, that's why I'm writing this is for the cross section shown in the figure, shown in the figure. Sir, which figure? This figure. So therefore, when I equate these two fluxes over here, at the center we know it is b naught into pi r square, and at the end we know b horizontal we need to write, or already we have derived the flux value, right? So b horizontal, that is b naught by 2 into r dash pi r dash whole square, pi r dash square, right? So when you do this pi r dash square, so you know the, like clearly you can see this pi will get cancelled, b naught will get cancelled. So this r dash, okay, this r dash, whatever this r dash that is there, so this r dash will become root 2 times of r. So this is also one very very important result, that the field line that is at a distance r from the axis of this solenoid, while it is exiting, it will be at a distance of what? Root 2 times of r. Okay, the field line that is over here, which is at a distance r from the axis, now it will be exiting at a distance of what, r dash, and that r dash we have put it as what, root 2 r. That r dash we have put it as a what, root 2 r. So I hope all these points are very much, pretty much clear for you. So this is a very important question and concept. So you can learn many things. You can learn about the non-uniformity of field lines in a long solenoid at the end. Okay, at the end of the solenoid. Also, you can understand very important things about like what, magnetic flux. Okay, so I hope all these points are. I hope all these points are pretty much clear for you.